Thank you. So, can you see my screen?
Yes, very good. We hear you well. Thanks.
Thank you. So I will start my presentation. Thank you for introducing me. I'm a Daiki Sekizawa, a doctoral student of the University of Tokyo. Today's presentation title is Decomposing Thermodynamic Dispersion of the Neural Dynamics via Spatio-Temporal Oscillatory Modes. And today's content is available on arXiv under the same title. In the brain, oscillations of different frequencies are widely observed in neural activity. Famous examples are alpha wave and beta wave, and so on. These different oscillations are associated with different brain states. In our study, we investigate the difference in oscillation between awake and anesthesia. Oscillation in these brain states are different, and it is known that the oscillation during anesthesia is much slower than oscillation during awake state. To understand brain information processing, the entropy production rate may be a promising tool. And its relation to various information processing is a recent hot field, and some has been applied to biophysics. For example, thermodynamic speed limit or thermodynamic uncertainty relations. However, relationship between oscillation and entropy production rate is unknown, despite its potential utility in neuroscience. In our study, we derive a novel decomposition of the housekeeping entropy production rate, which will be explained later, into oscillatory modes. Next, by applying our decomposition into neural data, we elucidate the difference in the oscillatory origin of the entropy production rate in the brain between awake and anesthetized states. Here we explain the problem setting. We assume a linear Langevin process for a real-valued state vector x. Note that linearity is assumed for the simplicity, but our theoretical result holds for nonlinear setting. This Langevin equation is equivalent to the Fokker-Planck equation, which describes the time variation of the probability distribution Px using the local mean velocity nu. The entropy production rate is defined as the expected value of the inner product of the local mean velocity. And in our presentation, bracket means the expected value taken for Px. To derive our theoretical result, we use a geometric decomposition of the entropy production rate proposed by Dechan, Sasa, Ito, 2022. The entropy production rate is decomposed into the excess part and housekeeping part. Excess part is a cost to change the distribution, and housekeeping part is a cost to maintain the distribution. They are similarly defined using the excess and housekeeping part of the local mean velocity. An excess part of the local mean velocity satisfies the same time variation of Px as the total local mean velocity. On the other hand, housekeeping part does not change the distribution. Therefore, excess entropy production rate is a cost to change the distribution, and housekeeping entropy production rate is a cost to maintain the distribution. Here we explain our main result. We derive a novel oscillatory mode decomposition of the housekeeping entropy production rate. The housekeeping entropy production rate is decomposed into the sum of the product of the frequency squared and the normalized intensity of oscillation. It means that oscillatory modes with a higher frequency and a larger normalized intensity contribute more to the housekeeping entropy production rate. I explain the meaning of the frequency and intensity of the oscillation in the next few slides. As a mathematical trick to derive our decomposition, we consider the virtual dynamics, which is defined using new HK of the original dynamics. And S here denotes the time evolution in the virtual dynamics. These two dynamics have the same new HK. Therefore, we can analyze the housekeeping entropy production rate of this original dynamics using this virtual dynamics. We also introduce a dynamic mode decomposition, which is helpful to understand our decomposition. And DMD is a method to decompose time series data into several spatio-temporal oscillatory modes. For example, the time variation of two-dimensional fluid dynamics can be decomposed into the sum of these oscillatory modes. And unlike Fourier transform, DMD incorporates a spatial pattern which is similar to the principal component analysis. Now I explain why our decomposition is interpreted as an oscillatory mode decomposition. Time evolution of the X in the virtual dynamics is written in this form. Using the spectral decomposition, it is decomposed into the sum of modes. And since nu hk does not change the distribution, the eigenvalue lambda is purely imaginary. So these are oscillatory modes. And we define the phi as frequency. And we also define the intensity of oscillation as the variance of this term. And this decomposition is a reminiscent of the dynamic mode decomposition, meaning that the dynamics is decomposed into the sum of oscillatory modes. And this frequency and intensity appears in our decomposition, and we identify the contribution of each mode to the housekeeping entropy production rate. For the derivation of our decomposition, I skipped the most of the part, but roughly it is derived using the spectral decomposition in a similar way. To get insight into our decomposition, we prepared a toy example for a trivial case. We consider a 2D particle which receives a rotational force and a spring force. In a steady state, mean and covariance matrix converges to these values, which are determined by potential by the spring. Then the partial dynamics is driven by the non-conservative rotational force. Eigenvalues and normalized intensities are written in this form, which constitutes our oscillatory mode decomposition with eigenvalue and the normalized intensity. Next, we applied our decomposition into neural data of monkey to investigate the difference in the oscillatory origin of the entropy production rate in the brain between awake and anesthetized state. In neuroscience, awake and anesthetized states are known to have different brainwave characteristics. For example, during awake state, alpha wave, which is 7 to 13 Hz, is observed. On the other hand, during anesthesia, the delta wave, which is 0.5 to 4 Hz, is observed. We compare the result of our decomposition between these two brain states. We use the data during awake and anesthetized state recorded from a 64 electrode, which means 64 dimensions. First, we explain an example in awake state. In the figure, 32 modes are shown, and since the data is 64 dimensions, there are 64 modes, but the mode with the same absolute value of the frequency are combined in the figure. And we can see the contribution from the 6.9 Hz, 5.9 Hz, and so on. And some of these contributions recover the total housekeeping entropy production rate. And since I in our decomposition is the index of electrodes of neural recording, we can also explore the spatial distribution of the modes in the brain. Now we compare the result of our decomposition between awake and anesthetized conditions. In the plot, frequencies are binned into delta wave, theta wave, alpha wave according to the conventional definition in neuroscience. We found that the main oscillatory source of the entropy production rate is different across brain states. In awake state, contribution from the delta wave is half of the total entropy production rate, and the theta and alpha wave account for the other half. On the other hand, in anesthetized state, the delta wave dominates the total value. These are robust across different anesthetic agents, although the total value depends on the anesthetic agent. I summarize today's talk. As a background, oscillations in the neural activity play a crucial roles in brain information processing. So we derive a novel oscillatory mode decomposition of the housekeeping entropy production rate into the contribution from the oscillatory modes. By applying our decomposition to neural data, we found that oscillatory origin of the housekeeping entropy production rate is different between awake and unassisted conditions. This is all. Thank you for listening.